What's up, guys? Welcome back to another Algebra 2 instructional lesson as we continue our exploration of zeros and graphs of polynomials here with Mr. Gaines. Last time we took a look at factoring polynomials and we looked at the rational zeros theorem, where we took the list of potential zeros that would be rational zeros from an infinite list down to a set number. We're actually going to combine those two ideas here today. So let's go ahead and take a look at problem number 4 in your notes. It says find all rational zeros of the given function. So we want to find the rational zeros here, which means we want to set the equation equal to 0 and solve if we can. Now, one of the methods that we've explored working with this has been factoring. Unfortunately, we don't have any techniques to factor P of x in 4a directly because it is a quartic polynomial. It has more than 3 terms. It's not a trinomial, so we can't break it down into 2 binomials. It's not a difference of 2 squares or a sum of 2 squares. It's too many terms. It's an odd number of terms. We can't group it without some very creative manipulation. So what we're going to do is we're going to look for possible rational zeros. Remember, possible rational zeros came of the list P over Q, where P is factors of the constant and Q is factors of the leading coefficient. So factors of the constant would be 4, so 1 and 4, 2 and 2. And factors of the leading coefficient, 3 is 1 and 3. So what I would get is factors of 4 over factors of 3. So 1 over 1, which is 1. 1 over 3, which is 1/3. Then I would have 2 over 1, which is just 2. 2 over 3, which is 2/3. 4 over 1, which is 1. And 4 over 3, which is 4/3. These don't have to come in any particular order as long as we include all of these. So any of these values could be potential zeros for our function. Now, what we need to do from here is figure out which ones are. So remember, we had the combination of the factor theorem and the remainder theorem in our previous lesson in PF.1 notes, which told us that if I take a number and I substitute it in for P of x, if it comes out, if my resulting figure is 0, then that number is a 0 of P of x. So to find all possible rational zeros, what I could do is one by one substitute each one of these numbers into P of x. So positive 1, see if it becomes 0. If it is, it's a 0. Then do negative 1. Positive 1/3, negative 1/3, 2, positive 2, negative 2, so on and so forth, doing positive cases and negative cases of each of these. That's going to take us a little bit of time. I'm going to show you a way that we can use synthetic division and factoring to simplify and shorten that process. So really what we want to do is we want to find one of them that works. So for right now, a method of guess and check could get us there. What I'm going to do is I'm going to pick one. And so I'm going to use 1. So 3 times 1 to the 4th power minus 1 to the 3rd power. And really, you wouldn't have to do these powers. It's just going to be 1. But just to hold consistency, I'm just replacing every x with a 1. And I'm going to do this on my calculator, which is fine. And I come up with 0. So I know that 1 is a 0 of the function. Now, from the factor theorem, I also know that x minus 1 is a factor. So what I can do is I can use this concept. Sorry, my computer just cut out here. Okay, that's better. I can use this concept to actually factor P of x. And then once I have the factors, now I can find all the zeros. So I know that, again, positive 1 is a 0. So I'm going to do synthetic division with positive 1. So I'm going to put the 1 on the outside of my synthetic division symbol. I'm going to take the coefficients of P of x and put those on the inside. So 3, negative 1, negative 8, 2, and 4. My remainder I already know should be 0, because that was the value that I got when I substituted 1 into the function. So I'm going to complete the process of synthetic division. Add down the column. There's nothing to add to 3, so I'm just going to drop the 3. Take 1 times 3, put that in the next column. So then I have negative 1 times 3, add down the column, that's 2. Take 1 times 2, put that in the next column. Add down the column, that would give me negative 6. Take 1 times negative 6, put it in the next column. Add down the column, that gives me negative 4. Take 1 times negative 4, add down the column, and that does give me 0. So the reason that I did this is because what this does is it factors P of x. We know that P of x is, one of the factors is x minus 1. X minus 1 because that gives me the 0, positive 1. The remaining factor would be this quotient, this quotient here that we get through synthetic division. So this is something we worked on in the last unit. This would be 3x cubed plus 2x squared minus 6x minus 4. So I can rewrite P of x as x minus 1 times this 4-termed polynomial. Now, if I can factor this 4-term polynomial, things get a little bit easier. And what we may notice is that, yes, this is a 4-term polynomial, which means I can probably group it. So let's try to group it. So I'm going to group the first 2. And I'm going to group the last 2 here. So my x minus 1 is staying the same out there in front. I'll come back to that later. Now, if I group, my GCF for that first group is an x squared, which would leave me with 3x plus 2. Then my GCF for the second group would be negative 2, which would leave me with 3x plus 2. This is good. So now my factors are x minus 1, still out there in front. X squared minus 2, my coefficients, and 3x plus 2. Finally, if I wanted to factor this a little bit further, I would get x minus 1. This is a difference of 2 squares. X plus root 2, the square root of 2 is just square root of 2. X minus root 2, and 3x plus 2. So here is the entire factorization for P of x. So it is these 4 linear factors. We know we needed 4 because we had x to the 4th. And now we've used the possible rational roots theorem and factoring to completely factor P of x. Now the question said to find the rational zeros. So this factor, x minus 1, is going to give me a rational 0 of positive 1. I would set 3x plus 2 equal to 0. Subtract 2, so 3x would equal negative 2. So it's going to give me a rational 0 after I divide of negative 2 over 3, something that can be written as a fraction. Now I would get zeros from x plus root 2 and x minus root 2 if I set those equal to 0, but those are irrational numbers. Square roots are irrational, so I don't need to include those in the list. So my 2 rational zeros would be 1 and negative 2 over 3. Let's try to use this process again in B. So in Q of x, if I want to find the zeros, the easiest way is to factor it, then take a look at those factors, set those factors equal to 0. Not going to be able to factor this one the way that it's written. It's x to the 5th power, a quintic here, and it has 5 terms, so we are not going to be able to group. So I'm going to go ahead and take a look at possible rational zeros. P over Q. So it's plus or minus the factors of P, which are factors of the 12, the constant at the end, over factors of Q, which is the factors of the leading coefficients, which is just 1. So just factors of 12. 1, 2, 3, 4, 6, 12. So positive and negative values of these numbers would give me, one of these at least has to give me a 0, okay, if we have rational zeros. So let's try to substitute. 1 to the 5th minus 3 times, try this again. 1 to the 5th would just be 1. Minus 3 times 1 to the 4th would just be 1. Plus 3 times 1 to the 3rd would be just 1. minus 5 times 1 squared is just 1, so 5, and then plus 12. And we're going to see that positive 1 does not work. So if I substitute in positive 1, it's not going to come out as I want. If I substitute in negative 1, let's take a look. Remember, we're looking for the result of the substitution to be 0. If the result of the substitution is 0, then that value is a 0. If the result of the substitution is not 0, anything other than 0, then the value is not a 0. So now I substitute in a negative 1, and negative 1 comes out to 0. So I'm going to go ahead and know that negative 1 is a 0, and I'm going to do synthetic division with negative 1. So using my coefficients for x to the 5th, that would be 1, negative 3, 3, positive 3, negative 5. Notice it skips x to the first power, so I've got to make sure I include a 0 for that placeholder for x to the first power. My remainder should be 0, so let's go ahead and add down the columns, then multiply by negative 1, put that in the next column, going through this process of synthetic division. So every time I add down the column, I multiply the result by negative 1 and put that multiplication into the next column, and then continue to add down the column, multiply by negative 1, put it in the next column, and it does give me a remainder of 0. So I know that one of my zeros is going to be x equals negative 1. I'm going to come back to that. Now, instead of writing q of x this time as all of the factors, I'm just going to look at what's left over. So this would be x to the 4th minus 4x cubed plus 7x squared minus 12x plus 12. And what I would like to do is to be able to factor this version, or what's remaining here, from synthetic division. But I can't. What I can do is I can go back to the list of P over Q and see if one of these numbers is going to work here with my new expression. So let me try maybe 2. Now I'm going to take what's left over here and see if 2 is a 0 for that number. So 2 to the 4th minus 4 times 2 to the 3rd plus 7 times 2 squared minus 12 times 2 plus 12. So when I did synthetic division the first time, it gave me a result I did not know how to factor. So I went back to my list of P over Q and tried to find another 0. 2 is a rational 0 for this value. I substitute in 2 and it comes out to 0. So now I'm going to do synthetic division again. Instead of rewriting synthetic division symbol, I'm just going to continue where we left off on the previous one. So there's all of my coefficients. They're all listed there. So I'm going to go ahead and just leave them. I'm going to do synthetic division again with that quotient, using 2, knowing that I want my remainder to be 0. So bring down the 1. 1 times 2 is 2. That goes in the next column. Add down the column. That gives me a negative 2. Take negative 2 times 2, which is negative 4. Put it in the next column. Add down that column. That gives me 3. 3 times 2 is 6. Put that in the next column. Add down that column. That gives me negative 6. Take 2 times negative 6, which is negative 12. Put that in the next column. Add down the column. It gives me 0. So far I've come up with 2 zeros. X equals negative 1. X equals 2. Now what's left over here is x cubed minus 2x squared plus 3x minus 6. So now I want to factor this if I can. So we may see that this has 4 terms, so grouping might be an option to go here. I can take out the GCF of x squared in the first group, which would leave me with x minus 2. Can take out a GCF of 3 in the second group, which would leave me with x minus 2. And now I can go ahead and factor from here. So this is going to be x squared plus 3 times x minus 2. If I wanted to factor this a little bit further, this would be x plus root 3 times x minus root 3, which is going to be irrational, and then x minus 2. So my zeros, I would have a 0 that is x equals -1. That's the first one that we found up here from synthetic division. I'm going to have an x equals 2. That's the second one that we found from synthetic division. I'm going to have x equals 2 again, so I can list that a second time if I want to list, if I want to list that a second time. We're going to see why that's important to know that it happens twice eventually here. And then I would have x equals √3 and -√3, which both of those would be irrational, so I would not need to include those. Okay? So what we did, again, was we used the possible rational roots theorem to identify numbers that could be rational zeros for our function. Then we substituted those numbers into the function to identify one that is in fact a 0. Instead of trying every number in the list, out of this there would be 12 numbers, all of the positive case and all of the negative case, we took one that worked and we did synthetic division. Now the result of that synthetic division was again something that we could not factor. So we tried another number from the list. I strategically chose 2 because I knew it would work. When I found out that that was a 0, I did synthetic division and came up with a quotient that I then knew how to factor, and then from factoring I can choose whatever zeros left are rational. Okay, so we can use a combination of factoring skills, synthetic division, and what we know about possible rational zeros, P over Q, to factor what would previously be extremely complicated polynomials. Now, the next thing that we're going to look at is what we talk about with polynomials and in behavior. So polynomials and in behavior. In behavior, we have talked about before previously, the key features is basically what goes on at the ends of the graph. So what I'm going to do here is I'm actually going to pull up Desmos, and we're going to take a look at Desmos. So I'm going to go ahead and I'm going to make a polynomial. Let's call this one x cubed plus 2x minus 1. It's my polynomial. And let's make another polynomial. Let's make this negative x to the 5th, or x to the 4th, plus 2x squared. And that's good. Let's make another polynomial. Let's call this one negative x to the 5th. Let's call this plus 4. And then let's do one more. Let's call this one x to the 12th power plus 4x to the, 4th power minus 3x plus 1. We're going to take a look at these 4 graphs. So let me first start with the x to the 3rd graph. X to the 3rd plus 2x minus 1. If we take a look at the in behavior, we know it goes up to the right and down to the left. If I look at any of my other graphs, none of those go up to the right and down to the left. Let's take a look at the third option here, x to the negative 5, because it kind of had a similar nature in the in behavior. X to the 3rd went up to the right and down to the left. X to the 5th went down to the right and up to the left. So it did the opposite. Let me take another one and let's make this x to the 7th. Just x to the 7th, nothing else. Notice this in behavior for x to the 7th matches the first one. Up to the right, down to the left. If I put a negative in front of it, that would reflect the function, and now it matches the in behavior for the third one. So what we see here is some commonalities. Take a look at the degree of each one of these. The degree of each one of these is odd. Their ends go in opposite directions. Take a look at the other two. Their degrees are even. Their ends go in the same direction. So the x to the 4th, both of the ends go down. The x to the 12th, both of the ends go up. They go in opposite directions though. So x to the 4th is going down, x to the 12th is going up, and the reason for that is the negative in front. Now let me put these graphs in here that are both negative. Notice that they're doing the same thing on the right side of the equation. They're both going down. Let me put in the graphs that are positive leading coefficient. They're both doing the same thing on the right side of the equation. They're both going up. So we have some rules for in polynomials and their in behavior based on the degree of the function and the leading coefficient. So here are our possible options. We could have a function with an even degree, a positive leading coefficient, or negative leading coefficient. Odd degree with a positive leading coefficient, or negative leading coefficient. So the in behavior, I wrote it formally for you, and I will write it formally for you again. As x goes to positive infinity and as x goes to negative infinity, what happens to the left and what happens to the right? Is it going up or down? So if it is a function that has an even degree, they go the same direction. The positive leading coefficient tells us what's happening to the right. So if it's even degree positive leading coefficient, y is going to go to positive infinity to the right. If it's even degree, they're going to go the same direction, so y is going to go to positive infinity as well to the left. So the ends are going to go up and up in both directions. So to the left and to the right, it's going to go up for both of those. So this would be the official notation, but if you remember up and up, that's good. For an even degree, negative leading coefficient. Even degree tells us they go the same direction. Negative leading coefficient tells us what happens to the right. So if it's negative leading coefficient to the right, we're going to negative infinity. We're going down. If it's even, I'm going to do the same thing on the left. I'm going to go down. So this one would be down and down. Down to the left, down to the right. If it's odd degree, odd tells us that the ends go in opposite directions. The leading coefficient tells us what happens to the right. So positive leading coefficient means go up to the right. Y approaches negative infinity or positive infinity. Odd means do the opposite to the left. So y would approach negative infinity. So this would go up to the right and down to the left. Finally, odd degree and negative leading coefficient. Again, the leading coefficient tells us what happens to the right. The odd degree tells us it's going to go the same direction. So opposite directions. A negative leading coefficient says y is going to approach negative infinity to the right. An odd degree says it's going to do the opposite to the left, so it's going to approach positive infinity. So this is going to go down to the right and up to the left. So in problem 5, it says determine the in behavior for each of the following functions without graphing. Correct notation is not required. So what I'm going to take a look at here is the leading coefficient. Is it positive or negative? Then the degree. Is it odd or even? So for 5a, the leading coefficient is positive, which means to the right I'm going up. The degree is even, which means I'm going to do the same thing going to the left. Now I can check this by taking a look at the graph. So here I have the graph of g of x. Let me zoom out a little bit so we can see that to the left it's going up, to the right it's going up. I can change anything that I want in between those two, or I can change anything on this graph that I want other than the leading coefficient and the degree, and nothing will change. So notice I'm messing with a lot of stuff. Nothing in the in behavior will change. It's going up to the left and it's going up to the right, regardless of what I change with the rest of the function. So the only thing we're focused on for in behavior is leading coefficient and the degree of the function. Let's go ahead and take a look at another one. In B, we have negative 2x to the 5th minus 5x cubed minus 3. So I'm going to look at the leading coefficient. It is negative, which tells me to the right I'm going down. Then I'm going to look at the degree. It is odd, which tells me to the left I'm going to do the opposite. I'm going to go up. Let's check this with the graph. It does match. To the right, I'm going down. To the left, I'm going up. Again, I can change anything that I want in between those numbers, and it does not change the in behavior. This looks crazy, but to the right, let me make it a little less big there. To the right, it's going down forever. To the left, it's going up forever. Go ahead and pause the video and see if you can do C. So for C, the leading coefficient was positive. So to the right, it's going up. The degree was odd. So to the left, it's going the opposite. So this should go up to the right and down to the left. So if you can memorize what I have written up here for the in behavior rules, that's great. But if you remember, the leading coefficient, if it's positive or negative, tells you if it's going up or down to the right. The degree tells you if the left is going to do the same or the opposite. And this is how we are starting to transition from just looking at zeros of polynomials and now getting into the graphs. This is a good place to stop for today. As we come back together with the next lesson, we're going to start to take a more in-depth look in graphing functions and actually get some polynomial graphs down on the page. As always, thank you guys for tuning in, and I'll see you soon.